Hi, my name is Anthony, and for my final project, I explored credit card fraud detection using several data mining techniques, including dimensionality reduction, tree-based models, and neural networks. The goal was not just to build an accurate classifier, but to understand how different techniques behave in a real-world, highly imbalanced dataset. In this presentation, I will go through my problem definition, a dataset description. We'll discuss my pre-processing and exploratory data analysis, dimensionality reduction, the use of decision tree and random forest, neural networks, and then we'll do a model comparison and discuss the metrics, and then I'll do a code walkthrough. The purpose of this project was to demonstrate why proper pre-processing and evaluation metrics and model selection are critical for detecting credit card fraud in a real-world, highly imbalanced dataset. This is fundamentally a binary classification problem, where the goal is to identify fraudulent credit card transactions. The challenge is that fraud is extremely rare. In fact, in this dataset, only 492 out of nearly 285,000 transactions are classified as fraud, which means accuracy alone is misleading. A model that just always predicts not fraud would be over 99% accurate, but also completely useless. So the main questions I wanted to answer here were, how do different models handle extreme class imbalance? Which techniques offer the best balance between catching fraud and avoiding false alarms? And how useful are techniques like PCA for understanding this data? Hi, Anthony from the future. I'm going to interrupt myself real quick because after I made this whole video, I realized I'm going to use a lot of terms that I should probably define right here at the beginning of the video. So let me do that now. Starting with PCA, Principal Component Analysis. PCA works by finding the directions in the data where variance is highest, and it rotates the feature space so that those directions become the new axes. The first principal component captures the most variation, the second captures the next most, and so on. In practice, PCA helps visualize high-dimensional data and can reduce noise, but it doesn't always improve classification performance, as we'll see in this project. Next is SMOTE. You're going to hear me refer to this a lot. It's Synthetic Minority Oversampling Technique. SMOTE is especially useful when the minority class is extremely rare, like fraud cases in my analysis. Instead of copying the same fraud examples over and over, which can lead to overfitting, SMOTE generates new, slightly varied versions of real fraud samples. This helps models learn the minority class boundary more effectively. I applied SMOTE only to the training set to avoid leaking synthetic data into the test set. Throughout this course, we've used the term ROC-AUC quite a bit, but I realized I should probably define that also. ROC-AUC is Receiver Operating Characteristic, Area Under the Curve. ROC curves plot the true positive rate against the false positive rate at every threshold. AUC summarizes that entire curve into one number. An AUC of 0.5 means random guessing, and 1.0 means perfect separation. It's especially valuable in imbalanced data sets because it doesn't depend on any one threshold. In my project, the random forest achieved an AUC around 0.98, which is excellent. And last but not least, I also wanted to talk about the F1 score. F1 score is a great metric for imbalanced problems because accuracy can hide failures, and precision or recall alone can give a misleading picture. Precision answers of all the transactions flagged as fraud, how many really were fraud? Recall answers of all the fraud cases, How many did we catch? F1 combines both, and in my results, the random forest achieved the highest F1 score, showing it had the best balance. But anyway, let's get back to my original presentation. Sorry about the interruption. For the data set itself, I used the credit card fraud detection data set from Kaggle. It contains transactions from European cardholders over the course of 2 days in the year 2013. The data set has 31 columns. The features V1 through V28 are anonymized and already PCA transformed for privacy. The time, amount, and class columns are interpretable, where class is the fraud label. There are no missing values, so pre-processing focused on scaling, splitting, and dealing with the class imbalance. Now let's talk about my pre-processing and exploratory data analysis. I performed a stratified 80-20 train test split to preserve the fraud ratio. All features were scaled using standard scaler, which is important for models like logistic regression, PCA, and neural networks. For class imbalance, I used 2 approaches: class weighting for logistic regression and the decision tree, SMOTE oversampling on the training set, only for the random forest and neural network. For exploratory analysis, I visualized the class imbalance, the transaction amount distributions using a log scale, and a correlation heat map for a small subset of features. These plots clearly showed both the rarity of fraud and the overlap between fraudulent and non-fraudulent transactions. I applied PCA to the scaled training data primarily for visualization and to test whether dimensionality reduction could improve classification. The first 10 principal components only explain about 39% of the variance, which already suggests information loss. When plotting the first 2 components, fraud and non-fraud points overlap heavily, meaning PCA does not clearly separate the classes. When I trained logistic regression using only the first 10 components, performance dropped, especially precision and ROC AUC. So in this case, PCA is helpful for understanding the structure, but not for improving fraud detection accuracy. Moving on to the decision tree and use of random forests. I first trained a decision tree with depth and leaf constraints to keep it interpretable. While it detected a large portion of fraud cases, it produced a lot of false positives, resulting in very low precision. I then applied a random forest, which combines many trees trained on different samples and feature subsets. Using SMOTE to balance the training data significantly improved the learning. The random forest achieved the strongest overall balance with high precision and recall and the highest F1 score of all the models tested. This shows the advantage of ensemble methods for complex imbalanced problems. I also trained a neural network using multi-layer perceptron and SMOTE balanced training data. The neural network achieved strong results with a recall of about 80% and precision close to 70%. While it performed well, it slightly underperformed the random forest in recall and ROC AUC. This supports the idea that for tabular data like this, well-tuned ensemble methods can compete with or outperform deep learning models. When comparing all the models, several patterns emerge. Logistic regression achieves very high recall but poor precision. Decision trees are interpretable but underperform ensembles. PCA helps with visualization but hurts classification and performance. Random forest with SMOTE offers the best overall balance. Neural networks perform well but did not outperform random forest in this case. Overall, the random forest model represents the best trade-off for this problem. In the final section of the presentation, I'm going to briefly walk through my code. I'll explain the main libraries I used, how preprocessing and resampling were handled, and how each model follows the same train, predict, evaluate pipeline. This structure ensures a fair comparison across all techniques. In the first cell, I install imbalanced learn and import all of the libraries used throughout the project. These include NumPy and Pandas for data manipulation, Seaborn and Matplotlib for visualization, and a collection of scikit-learn models and metrics. I also import standard scaler for feature scaling, PCA for dimensionality reduction, SMOTE for oversampling the minority class, and MLP classifier for the neural network. Finally, I configure Seaborn styling and set float formatting for easier reading. In the next cell, I load the dataset from the local file creditcard.csv and display the first few rows. I then print out the dataset shape and the metadata. Here we can see that there are 284,807 rows and 31 columns with no missing values across any columns. The class distribution output shows the extreme imbalance. 284,315 non-fraud cases and only 492 fraud cases. That's about 0.17% fraud. Then I begin the exploratory data analysis. First, I compute summary statistics for the time and amount features. The box plot of amount class shows that while fraud tends to involve higher amounts, the distributions overlap significantly. Next, I plot a class distribution bar chart which visually underscores how rare the fraud cases are. Finally, I generate a correlation heat map for a subset of features. Since the V features are PCA transformed, we don't expect intuitive correlations, but this still gives a sense of the relationships among the visible variables like time and amount. In the next section, I separate features and labels and create an 80-20 stratified train test split to preserve the fraud ratio in both sets. I then apply standard scaler to all features. Scaling is critical here because PCA and neural networks are sensitive to feature magnitude, and logistic regression also benefits from standardized inputs. Next is SMOTE. I apply SMOTE only to the training data to avoid data leakage. Before SMOTE, we have 227,451 non-fraud cases and only 394 fraud cases in the training split. After SMOTE, both classes contain 227,451 samples. This ensures that the models trained later, such as random forest and neural network, are not overwhelmed by the majority class. I defined a helper function called evaluate_model. This computes accuracy, precision, recall, F1, and ROC AUC. It prints a classification report and generates a confusion matrix heat map. I store each model's results in a list so that later I can create a comparison table. This function ensures consistent evaluation across all of the models. Here's the baseline model, logistic regression with class balancing. The model achieves extremely high recall, about 92%, which means it catches almost all the fraud, but precision is only around 6%, meaning it generates many false positives. The confusion matrix shows the same pattern. Almost all fraud cases get flagged, but many normal cases are also incorrectly labeled as fraud. Then I train a decision tree with a limited depth and class balancing. Its recall is slightly lower than logistic regression, and precision remains very low. I also plot the top 15 feature importances. Decision trees provide interpretability, but they don't perform well in this problem due to nonlinear patterns and extreme imbalance. Next is the random forest trained on the SMOTE resampled training data. This is my strongest model overall. It achieves precision of about 77%, recall of about 85%, an F1 score around 81%, and ROC AUC around 98%. This represents the best balance of detecting fraud while minimizing false alarms. The feature importance plot again highlights several PCA-based V features as key drivers. I apply PCA with 10 components. These 10 components explain about 39% of the variance in the data. The 2D PCA projection shows a heavy overlap between fraud and non-fraud classes, which tells us that PCA cannot fully separate the classes. When I trained the logistic regression using only the first 10 principal components, the performance declines significantly, especially precision, showing PCA is useful for visualization, but not for improving fraud detection accuracy. Then I train a neural network using MLP classifier with 2 hidden layers. The model is trained on SMOTE balanced data and uses ReLU activations with the Atom optimizer. The network performs well, strong recall around 80% and precision around 70%. However, it still does not outperform the random forest in terms of balance and performance. At the end, I compile all of the model results into a comparison table sorted by recall. This confirms the takeaway. Logistic regression achieves extremely high recall, but terrible precision. Decision trees underperform. The PCA model performs worse than the baseline. Random forest with SMOTE is by far the top performer, and the neural network is close, but still slightly behind the random forest. The notebook ends with a short qualitative summary. My class imbalance dominates the problem and requires special handling. PCA offers insights but not accuracy gains. Decision trees are interpretable but weaker. Random forest with SMOTE offers the best practical performance, and neural networks benefit from SMOTE and can perform strongly on tabular data. Thank you for taking time to listen to my presentation. I really enjoyed this class. I've learned a lot, including some tricks about how to make these videos. And I would love to stay in touch with anybody who's interested. So if you'd like to reach out, my information's right there. Feel free to contact me. Thanks. Bye.